So now I'm placing, well, the domain now is a circle, no longer an ellipse, and I'm placing one of the 2 points on the circumference of the circle, just as an illustration on the leftmost extreme of that circumference in this thing, and I'm running P across the boundary of the circle, and I'm plotting the envelope of the bisectors of the 2 segments PQ1 fixed here and PQ2 for some Q2 in the interior, right? So this is the envelope of the dotted red bisectors. Instantaneous envelope is T, and you get this delta shape thing. A well-known curve is perhaps this one when Q2 is right at the center of the system, and you get something of this sort. This is a well-known envelope or caustic that can be observed, in fact, at the bottom of coffee mugs with a little bit of water. You get this kind of specular caustic. I'll leave a link in the description for this effect. But what I'm looking for, as in the previous videos, are iso curves of area of this envelope as I move Q2 in the interior. So I've computed these, and they look like so. So there are these ellipse-like isocurves of area. So for example, if I run Q2 through this 0.125, so this is actually the fraction of this area with respect to the area of the red curve with respect to the area of the circle. So the area of the red caustic here, specular caustic, is 12.5% that of the outer circle. So if I run Q2 on this particular iso curve of area, you can look up here that the area is remaining more or less around that stated 12.5. Okay, if I go over to this one here, 34.3, you can see that up there. I'm reporting numerically what that area should be, and I am indeed staying true to that thing. So the geometry of these of this foliation of Q2 iso curves of area of the envelope is quite interesting. These curves are not ellipses. I've tested these with manual 5-point ellipse fits in GeoGebra. And in fact, if I actually try to put 5 points in some curve here, you're going to see that the corresponding ellipse, not only does it not closely match the boundary, but it actually escapes through the left side of the circle, meaning that these are not true ellipses, and this is a foliation of curves. Another thing that I saw here is that unlike with the elliptic boundary, I don't seem to be able to cause self-intersections of this envelope in the case of a circular boundary. So I always get these 4 cusps. This is a statement in itself. Can I prove that I always get 4 cusps, that I never get self-intersections if the boundary is circular? Okay. Another thing that I notice here is that the cusps, as I had wrongly reported previously, are not properly on the axes. Okay, they seem to be tangent to the axis. You can see here that there's a tangency point here, another tangency point there, but the actual cusp is away from that perpendicular axis through the midpoint of Q1 and Q2. And I think a similar phenomenon might be happening on these 2 other extremes here in general, namely that the curve is actually tangent to the axis, and the cusp does not lie in it, on it, right? So for example, if I move Q2 here, you can see here that the cusp is escaping that tangent. Now what happens if I now place Q2 elsewhere? Okay, do I get similar phenomena? Can I cause self-intersections? And the self-intersections tend to happen when you're near the boundary and there's some, not well-behaved situation where these 2 points are pretty close to each other, or they're very close to the boundary. But I don't seem to be able to cause self-intersections when the boundary is circular. And what I am seeing here again is this phenomenon that the cusps are not properly on the axes of Q1, Q2. but the curve does seem to be tangent to the axis. On both this case here and that case, it's apparent, and something like that might be happening on this axis as well. This is to be investigated. So there is some interesting, right, geometry here. There's a symmetric geometry, and I just wanted to mention on this video that I did compute these isocurves of area when one of the points is on the boundary of the circle. So you get this foliation of these algebraic curves, but they're not conics. All right, I'll see you on the next video.